Good afternoon, my name is Eduardo Marques. This is a webinar for the ISRM Commission on Preservation of Ancient Sites. And I will do a short presentation about a research that I'm developing here at Southeast Queensland about the weathering profiles of some igneous, metamorphic and sedimentary rocks as well. As I told, the summary of my presentation is a brief introduction to the weathering profile study, the morphology of the weathering profiles, which is one of the main purposes of this presentation, the motivation of this study, the scope of the study proposed, some results. I will not present all the results, but some of them, and the partial conclusions up to now. Weathering is a natural process which is responsible for the transformation of rocks into soil. This process is mainly composed by three kind of process. The first one is this order. There is nothing to do with the importance of the process. The first one is the biological weathering. Biological weathering is not considered into engineering problems because it commonly attacks small portions of rock masses, but it's very important when you are dealing with ancient sites or some specific sites problems. For engineering purposes, the two main processes are the chemical weathering and the physical weathering. What is chemical weathering? Chemical weathering is any process that transforms primary minerals that occurs in rocks into secondary minerals, mainly clay minerals, which is more stable under the physical chemical conditions that occurs in the Earth's surface or in its vicinity as well. So any mineralogical transformation occurring in a rock due to changes in temperature and pressure is related to chemical weathering. Physical weathering is mainly responsible for the comminution of the rock. Or in other words, the only but very important paper that physical weathering took into the weathering process is to break the rock. And more the rock is broken, more chemical weather can occur. So the physical weathering is not as important as the chemical one, but the physical weathering controls the chemical weather. Higher the physical weather, higher could be the chemical weathering. Chemical weathering depends on the mineralogy and the presence of water and temperature and pressure. For engineering purposes, these two, physical and chemical, are the most important because they produce larger amounts of soil. They transform larger amounts of rock into soil. When you are dealing with weathering for engineering purposes, the usual approach is to try to divide the rock masses into layers or zones with similar mechanical behavior. This can be done based on rock mass scale, on rock matrix scale, as we're going to see later today. According to Price, there are four types of weathering morphologies. The first one is the uniform weathering, that is mainly composed by a sequential division of the weathering profile into layers of similar mechanical behavior. So there is, from the surface into depth, you go from residual soil to sound rock. Cornerstone weathering is a type of weathering in which some rounded sound rock blocks are immersed into a soil matrix. And it's mainly related with igneous rock. Complex weathering is a type of morphology that is mainly related to metamorphic rocks, but not only related to metamorphic rocks. And is mainly, it is called irregular because the contacts between rock and soil masses and within different mechanical layers are very irregular because of the structural geology, mainly the presence of foliation, folds, fractures, and joints. So there is a lot of geological structures that controls the weathering, thus leading to this irregular shape of the contacts. And finally, we have the solution weathering that is mainly related to carbonatic rocks that can evolve to karstic forms. And this kind of weathering will not be discussed today because we are not working with carbonatic rocks. But it's an important one when you are dealing with this kind of rock. So here we have some examples of these morphologies. Here, and there on the far right, we have some cornerstone weathering examples proposed by some authors, Ruxon and Berry, Moy, Jerry Patton. Here and here we have some irregular or complex weathering morphologies, and you can see that the contacts between the layers are very irregular compared with the other one. And here we have what I have described earlier as a sequential weathering morphology, where you have several weather material layers from sound rock to residual soil towards the Earth's surface. Here you have some photos from some examples. This is a road cut in Brazil. You can see that you have some large core stones here. There is a guy here. This is a very complex, problematic weathering morphology because if you don't have a road cut or some cut that exposes this kind of weathering morphology, when you are drilling, you can take this contact here between this block and the soil as the rock top, and you can make some misunderstanding with the interpretation of this morphology as well. Here we have a very irregular morphology that is related to a Phylite in Brazil. This is a very steep slope. This is a Phylite, and you can see here that you have a large amount of rock and a small amount of soil. And some meters to the right, you have almost the opposite situation. You have a small amount of rock into the cut and a large amount of soil. So the contact between rock mass and soil mass is very irregular and controlled by some structures, or one structure. Here we have another kind of irregular weathering profile. This is a Itaberite, also in Brazil as well. And here we have some rock, not complete sound rock, but more related to slight weather. This is Itaberite. And you can see here that we have some very weather layers with some soils, some materials, which is that caused by the weathering along the foliation. So this block is pretty much stable because the cut is only over here. If you dip this cut, probably this layer will appear in the cut, and then this block can move. Okay. And here you have some another examples. This is a very complex weathering type of morphology, and this is a very common, very important one. Here we have some stress relief joints that are caused because as rocks are formed under high pressure due to plate tectonics and erosion, these rocks can move towards the Earth's surface, and because of this movement the confining pressure is reduced, and then the rocks dilates, and in this dilation process it's similar to a tensile being applied to the rock, and this rock can then break into a joint that is called joint relief, stress relief joint. And then you can see that there are several, like an onion ring over there. You can see that here you have some joints. And this joint has a particularity that is very important, that they are parallel to the Earth's surface. As the stress relief is the orthogonal to the Earth's surface, this fracturing occurs parallel to the surface. If the surface is flat, the fracture will be flat. If the surface is wavy, then the fracture will be wavy as well. And here what we can see is that you have a very steep slope, and these stress relief joints are parallel to the surface. Whenever you do a cut over there, this plane will intersect this cut, and then this mass can be unstable. Okay? And the problem is that this rock, by being formed due to a tensile load, its openness usually is very big, and because its openness is big, this kind of structure, they usually have water on it, and because they have water on it, the weather is very high within the stress relief joint. So it's usual to have sound rock, residual soil inside the joint, and then sound rock or moderated weather rock over it. And this is very important because the stability of this rock mass will be governed by this layer of residual soil, not by the rock that is here. Okay? So, what's the motivation of this study, to carry on this study? The identification of these geotechnical profiles and its morphology and its mechanical properties is important for several engineering works: cut slopes, underground excavation, slope stability, foundation, so on. And we cannot do proper design of these structures, these engineering projects, if you do not know how is the weather profile in your site area. So a better understanding of the weathering wherever it's important is an important issue that the engineers and engineering geologists should take into account. This context sets an important and complex stability mechanism of rock masses, and this is responsible by several accidents in Brazil, Southeast Asia, Africa. Whenever you have climates, a very rainy climate, and a very huge variation of temperature during the year or during the day, this is a very important mechanism because the soil production is higher under these conditions. Here are some examples in Brazil from my PhD thesis. Here there is a failure into a slope inside Rio de Janeiro urban area. You can see a car here. And when you look to things like this, it seems like this failure is mainly in soil. But when you get closer, you can see that it's all rock masses. The surface failure completely passes through the rock and through a stress relief joint inside this rock mass. So you can see here that you have a lot of planes. These planes are stress relief joints. That's the reason, because this structure is very important for the stability of these conditions. Here there was an accident that is called a mega disaster that occurs in Brazil, in southeast Brazil, during 2011 rainy season. You have several landslides in Petrópolis and Nova Friburgo area, and these landslides have killed more than 1,000 people. And this is a very common process in this area, also in Southeast Asia, very similar to the ones that occur in Hong Kong frequently, and several other countries. And when you see a picture like this, you can see that it seems like soil, but you can see that there are some of these that are developed in rock. And actually, most of them are developed in rocks because of the presence of this stress relief joint that I have mentioned before. So, when the study of weathering profiles started. Mainly the approach was to try to divide the rock mass into similar mechanical materials by using three parameters: soil rock ratio, rock discoloration degree, and the presence of original structures. Several researchers have done this, and because this model did not completely express the behavior of rock masses into the field, because no consideration of rock matrix properties were taken into account, another approach was proposed in order to give more attention to rock matrix. And several others researchers have done works on this rock matrix characterization, including me, okay, and with some colleagues in Brazil as well, within this paper here in engineering geology. But what we are trying to do here is use both approaches, because when you do just the rock matrix approach, where do you put this mechanical characteristics that you have defined through this characterization? Where do you put these values into the rock masses? You must know it. So in order to solve this problem, we are using both approaches. We characterize the rock masses, as I will show you, and we characterize the rock matrix, I will show you as well. So I have already done with some colleagues in Brazil this method, and the results were quite good. We have classified the rock masses, and we have taken samples, took to the lab, do some tests, and define the rock matrix properties as well. So we are using this proposed method here in Australia in different weather and climate conditions to see if it works. And we'll try to perform several field and laboratory tests, descriptions, and analysis in order to characterize the rock matrix. But the focus here was not to use traditional uniaxial compressive strength, triaxial, tensile strength, battery of tests. We are trying to see if there are some more easy and more fast tests that we could apply in the field and also in the lab in order to have this knowledge about the effects of weathering into these rock masses. So if you want to do a more detailed study, it can be done and it must be done. But what we are trying here in this step 2 is to perform some quick and easy tests in order to know if you can also achieve the same purpose that is described and define the morphology and the mechanical characteristics of the materials within the weathering profile. Why selecting these rocks? Which rocks I have selected? Sandstone, basalts, and phyllites. I have selected these rocks first because there is few or no knowledge regarding mainly phyllites and sandstone for rock mass and rock matrix scale. There are several works in rock matrix, but not too many work in rock masses. And for phyllites, there are not too many works in both scales. In basalt, we have several works in rock matrix, but we don't usually have too much work with rock mass. And so, as we are trying to put them all together, it's a good approach. And finally, I will try to provide some future correlation with weathering profile developed under subtropical climate here in Australia and tropical climate there in Brazil, when I'm back in Brazil. So here, what we are trying to do, how this rock mass transforms into this rock mass, and how this rock matrix transforms into this rock matrix. So we are using this rock mass scale and the rock matrix scale approach. So what we have done to define the degree of rock mass in the field. Sorry, there is a mistake here. So at the rock mass scale, we have to describe the rock matrix characteristics in order to divide the rock masses into similar mechanical behavior layers or zones. So what we are doing is do some visual and geological recognition procedures What's the mineralogy? What's the grain size? What's the fabric? What are the discoloration degrees? So we are using characteristics that other researchers have used in the past. And what's the mineralogical change? As we can see in the field, is there any original matrix structure or not? And also we are introducing some simple mechanical recognition tests, like what's the strength of the rock matrix against blows of the geological hammer strike? Is the material able to be manually excavated? Can we scratch the material with a pen knife or with a nail? What's the easiness of extracting some grains from the rock matrix? And if you are using borehole samples, how can you break an X or another size rock sample? Does the material disaggregates underwater? So all this kind of quality description that help us to understand what's the effects of weather. For the rock masses, the division of the rock masses can be based on several weathering classification. I like to use the ISRM classification. That's mainly based on the soil to rock ratio, discoloration degree, as I told you before, and then we can divide the weathering profile into layers of similar behavior based on this criteria. I think this is a very nice approach. The only thing that I should would like to point, is that there may be some misunderstanding between class 3 and class 4, because class 3 is lower than half of rock matrix decomposed to soil, and here more than half. When you have 10 and 90 or 20 and 8, it's easy to define, but when you have 45 to 45, 48 to 42, 52, it can be difficult to separate 3 to 4. So here, sometimes I prefer to use a more an intermediate classification, 3 to 4, 4 to 3, depends. Okay? So, we selected these three rock types. Phyllites were from here, in the neighborhoods of the University of Queensland. St. Lucia and Dorpil in Taringa neighborhoods. Sandstones were from Sunshine Coast. And basalts and tuff were from Mapleton Melanie Plateau. That's close here as well, 150 to 40 kilometers. I have selected 15 to 20 weathering profiles for each one of these rocks. From this total, I selected 5 to do a more detailed description and collect samples to lab tests. I have collected more than 600 kilos of rock samples, and I have two other concerns, which is the time that I had to carry on the research, approximately 7 months, and cost, as I need to do with a low-cost budget. Okay. Field works. What I try to do in the field, define the typical morphology of those rocks under subtropical climate. This was a very detailed work. This is one of the main goals of this work, this research. Perform a detailed description of rock masses and rock matrix, including fabric, color, structural geology, number of layers, and so on. Try to identify the main geological structure that controls the weathering. Determine the soil-rock ratio. Determine several discontinuity properties, including RQD, based on Palmstrom's suggestion, factoring the spacing index, and from this value, calculate the JV and the RQD, persistence, opening of the discontinuities, presence and type of filling material, and so on. Also, roughness, JRC, and JCS, based on Schmidt-Hammer tests. I have made more than 1,000 Schmidt-Hammer tests, and the results were very good, as I will show you later. In the lab, we have done physical characterization to determine physical parameters, brine saturated density, apparent porosity, and water absorption capacity. We have done microscopic description of 22 thin sections in order to determine the mineralogy, the weathering process in rock matrix scale, some index, microfractal index, which is the number of fractions for a 1 centimeter traverse, the micropetrographic index, percentage of sound material divided percentage of unsound weather material, and point load tests. We have done more than 200 point load tests in order to have some idea about the strength of the rock and its weathering materials. So these are the area of the study of the phyllites. In orange you have the phyllites, the profile that we have just visited. In yellow, the ones that we have selected to do a more detailed description. Here we have in blue, the sandstone profiles, in green, the basalts and tuff profiles. In light blue, the profile that we have collected samples in, done a more detailed study, and as well in the light green here for basalts. So here we have some examples. I present some results for the morphology of the 3 rocks and some lab tests for the phyllites. What we can see here, there is a foliation here that dips around 20 degrees. And what we can see is this stress relief effect acts like producing some discontinuities parallel to the foliation, so creating the stress relief joints. Whenever the foliation is horizontal, the stress relief joints will be horizontal as well, because the foliation is a weakness plane. So the weathering takes advantage of this weakness to create discontinuities parallel as stress relief joints. So in this case, the dip is approximately 0, so the direction of the stress relief joint will be approximately 0. Whenever the foliation dips, the stress relief joint will dip the same. What happens here is that when you have horizontal stress relief joint, these joints act like as contact between different weather materials. When you have inclined foliation, these contacts follow these discontinuities, but also the tectonic fractures that are approximately vertical have a high dip. So the contact here will be like a saw, some steps, and here will be more persistent along the joint, the stress relief joint. Here is for another example. So we have contacts that are pretty much following the stress relief joint, and whenever there is a tectonical fracture, the weathering dips into it, so undulates the contact. The undulation of the contact is due to the tectonical fracture, and the persistence and the majority of the contact pass through the stress relief joint. So here we have what I have. I go to the field, take some pictures, prepare this panoramic view, then I come back to what I've done, to come back to the field, and then in the field I have marked all the stress relief joint in yellow and the tectonic fractures in black, and then I have divided the weathering profile with these red lines here with several different weather materials. For sandstone, the same method was used. You can see here that we have some joints which is parallel to the bedding, not to the foliation anymore, because there is no foliation in sandstones. But again, the stress relief joints takes advantage of the presence of this bedding and develops discontinuities along this bedding in order to produce more weathered material. And these contacts, between these layers are mainly controlled by this structure for the sandstones. So here, the same case, we have the view, the general view of the profile, and based on this view and in the fields, I have made the division, the identification of the several weathering material that occurs along the profile. And again, we can